And the first talk is by Antoine Zakardjian about estimating the dense gas mass of molecular clouds using a spatial unresolved 3 mm line observations. Go ahead.
All right, thank you very much. So this talk is going to be, again, about molecular clouds and star formation, but with a focus on the estimation of molecular cloud properties from observation, and specifically on trying to infer the internal density structure of molecular cloud from line observation. So since there are both astronomers and statisticians in the room, I thought I could start things with a bit of a context regarding star formation theories. So our general understanding of things is that the interplay and competition between turbulence, gravity, and magnetic field is going to set the star formation activity of a cloud. Turbulence, in particular, is going to play two roles. It's going to both trigger and limit star formation. So this turbulence, coupled with magnetic field, is going to shape the molecular gas on large scale. And since this turbulence is supersonic, it will create shocks and regions of overdensities where then gravitational collapse can occur and star formation can occur. So I'm just showing here a snapshot from a numerical simulation showing the gas density. And you can see in red the very dense regions where star formation is happening. But this turbulence also limits star formation. The bulk kinetic energy, the chaotic mixing of this turbulence is going to limit the monolithic collapse of the gas on large scale, and it's going to slow down with magnetic field the collapse that is already occurring in small overdense region. So overall, this competition between gravity turbulence is the key regulator of star formation in molecular clouds. Now, one key result from numerical simulation is that this dynamical state of the cloud is actually encoded in the distribution of its density. Turbulence first is going to create this kind of log normal distribution. And so the stronger the turbulence gets, the more shocks there are and the wider the distribution gets. And then above a certain threshold density, gravitational collapse will take over and will tend to produce this kind of polar law tails at higher densities. Now, another thing is that these kinds of gas density PDF are now at the core of modern predictive models of star formation, with the idea that integrating this density PDF above a certain critical density will predict the star formation rate of a cloud. And so overall, that makes the gas density a key statistic that we want to infer from observation. And that is something that we can do directly in the case of Milky Way observation, simply because the proximity of Milky Way clouds allow us to map them in great spatial details. So one key result, for instance, is that indeed molecular clouds display this kind of log normal and polar law tail distribution, which again reflects turbulence and gravity. One more result is that regions that are actively star forming tend to all display a prominent polar law tail, whereas regions that are non-star forming or quiescent tend to be purely log normal. A final result from this Milky Way studies that I want to highlight is that the star formation rate of those Milky Way clouds tend to be proportional to the dense gas mass. That is the mass of gas above a certain universal density threshold. So overall, Milky Way studies of nearby clouds allow to access the microphysics, the details of the star formation process. But those observations lack the larger scale environmental, galactic, or even cosmic time context that is required to build a comprehensive theory of star formation and of DAOISM. So fortunately for us, this context can be accessed with extragalactic observation, as has been mentioned before today. But this context gain comes at the cost of the observation resolution. If you look at our closest neighbor, the Andromeda galaxy, that implies a decrease in linear resolution by 2 orders of magnitude. So as it has been said before, the emission that we observe in extragalactic observation is a complex mixture of different physical conditions, different physical environments. And so this beam mixing of the physical condition really makes the inference of gas properties very difficult. So all the motivation of this work was to try and solve this beam mixing problem in extragalactic observation, and specifically trying to infer the distribution of the gas current density that is average in a single pixel or in a single resolution element. Now that problem is basically an invert problem. Given a set of observation, in my case, line integrated intensities, 12CO, HN, and 2H+, and so on, I want to find the parameters that best describe those observations given a physical model. Now again, for Milky Way observation, we could expect a single set of physical parameters, a single density, a single temperature, and so on, to describe the observation. But because of beam mixing, there's not one set of parameters, but a full physical distribution that is full distribution of physical parameters that is average. And so we are starting with this to model the emission that we observe. We model it as the average of this distribution of physical parameter weighted by an emission function. And that emission function basically predicts the integrated intensity of a line L for a given set of physical parameters theta. Now stated like this, the problem is basically impossible to solve because it will require inverting distribution of unknown shape with a large number of dimensions with a very limited set of observations. So the first thing we had to do was to greatly simplify this problem to make it solvable. The first simplification we made was to focus on the most sensitive variable theta, and that is going to be the column density. That is both the parameter of interest, that's the parameter we want to derive, and it's also the parameters that drive most of the variation in the observation, as Mario Tafala showed, for instance, yesterday. And so knowing this, we simply drastically reduce the parameter space to the column density only. Now, the next challenge has been to derive this column density PDF from observation. The challenge is that we only have a very limited number of observations, so that greatly limits the number of parameters to be estimated. So the second simplification we made was to parameterize the column density distribution, which helped with the model degeneracy, but is also physically justified, as I said in the introduction. So again, we are going to assume that the density PDF is composed of a log normal driven by turbulence and a power law driven by self-gravity. And so this PDF can be described by four parameters, N0, which sets the mean of the log normal, sigma, which sets the width of the log normal, then a transition density between log normal and power law, and finally the power law index itself. So all those parameters describe the column density PDF that is averaged in a single pixel. There is a fifth parameter, A, which is basically the pixel filling factor of the molecular gas, but in our implementation here, it's simply a scaling factor on the emission. So the last missing piece now to complete this beam mixing or forward model is the emission function F. That could be anything. It could be a radiative transfer model like Frederick, like something that Antonio showed this morning. It could be a more complex numerical code. Now, in our case, we made the choice of an empirical emission function because we could build on the information given by the Orion B dataset. If you're in the room, I guess you've heard of this dataset before. If not, again, this is a quite unique wide field high-resolution survey of the Orion B molecular clouds. So it's about 20 by 20 parsecs in size with a pixel size of about 0.04 parsec and contains more than 30 molecular line detection. So it's overall a very rich and very informative data set that we can use to characterize line emission as a function of column density and to build this empirical emission function. So now in this right plot, I simply show the line integrated intensity of from top to bottom 12CO, HN, and N2H plus as a function of the gas column density. And so I simply bin the data by column density. So the black line shows the average trend, and the gray area shows the standard deviation in the bin. So we can clearly see this nonlinearity. We can see basically the same trends as what Mario Tafala showed yesterday. And this nonlinearity in the emission lines is going to be mostly driven by optical transfer effect, but also photodissociation at the very low column densities and chemical effects such as freeze out at higher column densities. So to construct the emissions function, I simply fit those relations for each line L in the dataset independently, and I use a combination of two power laws with a smooth transition. And so that yields this emission function, which maps from column density to line emission, and which encodes all the subcritical excitation and nonlinear behavior of emission lines. Okay, So with that, the forward model or beam mixing model is complete. But as I said, I wanted to solve the beam unmixing problem. So for that, I want to retrieve the PDF, the column density PDF from the observation. And to achieve this, I needed an inversion procedure. And for that, I made the choice of Bayesian inversion, and specifically a tool that has been developed by Pierre Palus, so a colleague from the DAOISM team. I will talk about this in much more detail tomorrow afternoon, I think. But basically, a few qualities of this implementation are that the Bayesian inversion accounts for both noise and calibration uncertainties. It also implements a spatial regularization prior on the parameters. And finally, it implements a local and global exploration of the parameter space. So here I'm just displaying as an example typical input and output of the method. So the forward model coupled with the Bayesian inversion. So my input here is just the Orion dataset, but I've averaged everything to a single pixel, as if the cloud were observed in an external galaxy. And that gives me, as an input, a vector of 8 integrated intensities. And on the right, I show the result of the inversion. So the blue region shows the different MCMC samples. The yellow dashed line shows the result of the inversion, so the column density PDF that best describes the observations. And then in red, you have the true column density PDF of Orion B that has been directly mapped with this continuum observation. So you can see the two match quite well. So the method seems to be working quite well, at least on this test case. And there is a lot more work that has been done to test the robustness, characterize the degeneracies of the model, all of which has been published last year in a paper. But for this presentation, I'm going to focus more on the outputs of the method. I'm going to showcase an application of the method to the scale of an entire galaxy to display the potential outputs and the insight that can be gained with this new method. So the target galaxy here is M51, which is this iconic grand design spiral galaxy that Sophia presented this morning. It's on the star-forming main sequence. It's relatively Milky Way-like in terms of star formation activity and metallicity. It's located about 10 megaparsecs away from us. And the observation here include evidently the SWAN dataset that again Sophia presented, as well as the post-observation of 12C0120. So there is overall 7 independent emission lines to characterize or to infer 5 parameters. Also, the pixel size is about 45 parsecs. So when I apply the method to this dataset, I get as an output the map of the different parameters that describe the column density PDF that are averaged in each and every single pixel of the observation. And so the first parameter that I show here, N0, is again the mean of the log normal. And that parameter is the most well-constrained one, simply because it's the parameter that drives most of the variation in the observation. And so you can see this trend of the gas getting denser toward the spiral arm ridges and the nuclear ring. Also, I should say that I've removed the very center of the galaxy because it's contaminated by an AGN, and so the model cannot reproduce the emission lines that we observe there. The second parameter that I show is the log normal width related to the turbulence of the gas. So it's also well constrained, but the spatial distribution is a bit more patchy. You can see hotspots around the ring of higher values of this sigma parameter, but there is overall this trend of the log normal width, so the turbulence getting higher toward the spiral arm ridges again and toward the nuclear ring. Now the last parameter that I show here is the roughly the critical density for colors, but really it's the transition between the log normal and the power law. And again, this parameter shows good spatial structure. I think that the takeaway here is that this parameter is far from constant. Here it varies by more than 3 orders of magnitude. It basically follows the N0 parameter. In fact, a good number of pixels, especially around the molecular ring, are purely log normal. And those shows up here as yellow or bright green pixel, because this transition density is so high, it's so far removed from the mean of the log normal that the power tail is basically negligible. Okay, so another thing that we can do is to look at the statistical distribution of those NPDF parameters. So I display them here as those gray shaded histograms. And for comparison, I've overlaid the distribution of the NPDF parameters of 30 nearby Milky Way clouds that have been directly mapped with dust continuum observation. And the first thing that we can notice is basically that the distribution of N0 is strongly bimodal. There's basically two cloud populations in M51, at least characterized by this parameter. One of lower column density, which is basically located in the interim region of the galaxy or at the edges of the spiral arms. And there is a second population, much denser, 10 times denser, which represent the molecular ring of the galaxy or the dense ridges of the spiral arms. And one thing I want to highlight is that those two populations of clouds and the distribution of NPDF parameters that we see in M51, they closely resemble the nearby Milky Way cloud that we see. In fact, this first population at lower density is very similar to the typical gold belt clouds that have been presented before, today and yesterday. And the second population at much higher density is much more like the more extreme environments, such as very dense infrared dark clouds that we see in the Milky Way, or high mass star-forming regions such as W4C3, or even sometimes clouds from the central molecular zone. I think what's striking also is the range of values that we infer, in particular for the log normal width. The range of parameters in M51 and in the Milky Way is the same, even though the parameter space explored was much larger than this. And I think the shape of the distribution is also quite similar. Now, besides investigating the shape of the NPDF, their distribution around the galaxy, another piece of analysis that is enabled by this method is the inference of new, dense, and polar gas mass estimate. For every pixel where a column density PDF is inferred, I can simply integrate this column density PDF above the desired critical density to get a dense gas mass estimate. So here I integrate above 7 times 10 to the power 21 to estimate the dense gas mass. That's a typical threshold for dense gas from Milky Way studies. And then I also compute the polar gas mass, so the mass of gas in this polar here, which we could consider the mass of gas that is subgravitating or actively collapsing. And so that's potentially a more accurate estimate of the dense gas mass than using single line traces, because this estimate builds from the complete shape of the column density PDF, and it also accounts from all the subcritical excitation processes that affect typical dense gas tracers such as HCM. So now this plot shows the distribution of those two parameters, and in particular the distribution of the polar gas mass at the scale of an entire galaxy for the first time. And from that, we can get key statistics, such as the total fraction of dense gas or polar gas mass, or the area they cover across the field of view. For instance, we can see that 70% of the total mass in this field of view corresponds to dense gas, but only 15% corresponds to polar gas mass, so potentially collapsing gas mass. So now, as I've said in the introduction, those dense gas masses are tightly related to the star formation rate of molecular cloud. To study this, I'm using the 21 micron emission from James Webb observation to get a rough first order estimate of the star formation rate of the galaxy. And that allows me to compare star formation rate, polar gas mass, and dense gas mass. And I think to first order, those three plots, those three figures, shows a good spatial match. I mean, if we look at regions that are forming a lot of stars around here, they also show large amounts of polar gas mass and dense gas mass. But it's more of a first order match. If we look more closely into more details, for instance, in the southern spiral arm of the galaxy, we will see regions where there is large amounts of gas, large amounts of dense gas, but little to no star formation activity. I've selected a few sightlines to illustrate this, but if you look at, for instance, sightline 2, 3, and 5, which are located here, here, and here, they all display very large amounts of dense gas, but no star formation activity. And all those distributions are purely log normal. On the other hand, if I look at the distribution from the sightline 1, 4, and 6, they all display strong star forming activity, and they all display a prominent polar tail. Another way to look at this more systematically is simply by looking at the correlation between star formation rate, again traced by the 21 micron emission, and those different mass estimates. So here, the mass of dense gas estimated with the method, the polar gas mass, and the HN emission as a reference. And so there is evidently a lot of scatter in those relations, but the correlation between polar gas mass and star formation is the most linear one. I mean, the slope is about 0.7, whereas for the dense gas mass, it's about 0.5, and for HN, it's about 0.6. In fact, if we look at the mass of dense gas against star formation rate, we can distinguish again the two populations of clouds in M51. So the first one at lower column density, which clusters here, and the second one at higher column densities, which clusters there, and is offset in this direction compared to the one-to-one relation. So the very simple takeaway here that I want to highlight is that the mass of gas in the polar tail of the PDF shows a more linear relation, and so it seems to be more closely associated to star formation than simply the dense gas mass. That's the only point I'm trying to make. And that was the last piece of analysis, and actually I wanted to showcase in M51. So to summarize, this first application of the method has shown that M51, the population of NPDF or column density PDF found in M51 is actually very close to what we observe in the Milky Way. Also, the region that exhibits strong star forming activity all display, or they seem to display a strong polar tail, whereas quiescent region, even though they can display large amounts of dense gas, tend to be purely log normal. And finally, the mass of gas in the polar tail seems to correlate better with the star formation rate than simply the dense gas mass. And now to finish, the main takeaway of this talk is basically this method itself. I mean, it's one of the first of its kind with the method that Antoine presented this morning. So it allows for the first time basically to infer the full current density PDF of the gas averaged within a resolution element, and that across the entire galaxy. And that allows subsequently to get new estimates of the mass of gravitationally collapsing gas, but also the dense gas mass, and to map these key properties for star formation series across the entire galaxy disk. So in the future, we'll try to use this method to help us understand how global galactic properties or larger scale environmental properties can affect or even set this gas column density PDF with a few key questions here that I've highlighted. So how does the NPDF relate to the cloud dynamical state, or how does the larger scale galactic environment dynamics kinematics can affect or set this column density PDF, or even simply where does the gravitationally collapsing gas accumulate in galaxies? Thank you very much.
Thanks, Antoine. We have several times for questions. Is Alvaro over there?
So thanks for a very interesting talk and very interesting method. I'm curious about the accuracy of each of the parameters that you derive. In particular, when you are, for instance, you describe this N0 and threshold. Mm-hmm. Because, I mean, even in this distribution, you have N0 defined by at least an order of magnitude more points in the PDF than the N threshold. So how these two things are, I mean, what is the relative accuracy between them and whether they could be potentially degenerated given also, for instance, in this distribution, the two distributions look pretty similar in terms of shapes, or they are nicely decoupled.
This one and this one?
And that one, yes.
Yeah. Those are pretty similar because, in fact, the parameter that I infer directly is this one. So it's the relative transition between power law and log normal. And this one is pretty much is not constant, but it varies basically between 2 and 10. And so this variation of Unresolved that we see is basically driven by the full common density PDF shifting to higher values, but with a relative transition that is staying the same. As for how accurate those measurements are, I haven't shown the error bars here, but there are some degeneracies in the parameters, not between this one and this one, but between, for instance, the width of the log normal and this parameter. So the good thing with the Bayesian inversion is that the degeneracy between the parameters and the error bars that go with it, even though I don't show them here, are easily to estimate afterwards. I'm just going to show a quick example if I can find it. Yeah, that's an example of degeneracy between two parameters. You have two column density PDF, one with a very large log normal width, and with a transition density between log normal and power law that is very far away. And you have a second one where the transition density is very early and the log normal width is much smaller. But when you look by eye, they are very similar. And for the model, they are very similar because at the end of the day, the integrated intensity of the line is sensitive to the integral of this, not to the detail of the parameter. And so you can see that the emission for those two column density PDF, even though the parameters are very different, the prediction of the models are very similar.
To follow up, so they are indeed very similar, but the physics is different.
Yeah, that's something that we cannot. That's a limitation of the model that we cannot go beyond. Just the averaging is going to induce a loss of information that we cannot recover, and that's a typical example of it. So when I estimate the parameters, let me go back there. Yeah, there is in the posterior distribution in the error bars this degeneracy that is accounted for. So if you're trying, for instance, to use this NPDF parameter to fit actual predictive models of star formation, that is going to be very difficult because the error bars on the parameter is going to be too large. But all the results that I show here are robust to this degeneracy because the difference is in the parameters, in the distribution is larger than the error bars that I infer.
Any more questions?
So in the method, when you try to connect all the different species, do you use the same line width for all of them? Do you need to assume that they all emit at the same volume? I think maybe that's in the next talk that you're going to give, but if you could give us some.
Yeah, so since it's all empirical, there is no prescription for the line widths or any radiative transfer parameters. It's really just fitting those empirical relations from the data between current density and line intensity and using them as the empirical emission function. So this function here is completely fixed. Okay. One potential way of going forward is to have a semi-analytical model, something like what Mario Tafala showed yesterday morning, where you can include the line width of the lines in the free parameters or the temperature or so on. But at the moment, there is no.
So in a way, you need to assume that those relations obtained from Orion B are universal.
Them. Exactly.
But in theory, that could change.
Yeah.
If you change the line width substantially, or if the feedback is different.
Yeah, I agree. Okay. So it could change substantially. The idea is that to first order is the current density that drives everything. If we look here, the emission increase, I don't know, for 12 it goes several orders of magnitude, but the scatter in a cloud like Orion B, where already there is a lot of different line widths and different temperature, the scatter is much smaller than the actual trend. So it's about sweeping any second order effects under the rug and focusing on the current density. I think for first order estimates, it's good enough. I could even say that it's not enough for sure in that regard, but it's probably already better than using a single line and conversion factor. It's a way forward.